So yeah, one word to rule them all, which is not entirely true, because we won't be using, we'll pretend to be using just one feature at a time, but it will, as you will see in a minute, it's a little bit of cheating here. We are sucking up also some context, not only the word itself, but also its context. So some other words from a corpus are also sort of present in our model, as you will see in a minute. So in authorship attribution, the goal is to compare one text against other texts collected in your reference corpus, right? So it is ultimately about comparing. So the nearest neighbor or the most similar text to our text in question is the author we are seeking for, right? So that's how it can be defined on a very basic level. I mean, what authorship attribution is about. And there have been many different approaches to this problem, starting from very basic features. At the turn of the 19th century, there were some ideas that the average word length might be a secret key to authorship, or average sentence length, or lexical density, such as type token ratio, or TTR. So these simple measures were hoped to show us more authorship idiosyncrasies, right? And then after a publication of Mostel and Wallace in the 50s, we learned quite a lot about the power of frequencies of the most frequent words. Not really most frequent words, but the function words. That's what makes them so interesting for us, because not only are they used subconsciously or not entirely consciously, but also they are very frequent, so their statistics is very rich. And we have learned how to use, say, 100 most frequent words, or 300 or 500 most frequent words to map the authorship landscape very reliably. And the downside of this kind of approach is that we totally disregard the context. So what we do, we basically cut off or cut up all the words from a text, and we treat them as a bag of words. So there is no connections between those words whatsoever taken into consideration, right? So the context is totally irrelevant here. And a very simple approach to extend this feature set to some context-aware features is to use anagrams, or combinations of 2 adjacent words, 3 adjacent words, this kind of chains of words that give us some idea of the context. And it turns out it doesn't really work. It doesn't work very well for authorship attribution. But the lesson we've learned is that if we switch to other features, not really lexical but grammatical features, such as grammatical categories of the words, not the lexical content of the word, but it's a grammatical category. It's what we're interested in here. So part of speech tags. Then we can combine them into pairs, into triples, into those combinations of n-grams. And there is again an idea how to get some context into the game. But then there came those very fancy representation of text using usually neural networks. And these are those representation in which the context is what makes the word shine. And this is word embeddings, or word-to-vec algorithm and other algorithms doing word embeddings. And we will be focusing on that approach in a minute. And this is, other neural network setups in which the previous context is relevant. So this is long, short-term memory, for example, neural networks, which are aware of what has happened previously, and they model the next word according to the previous context. And there's also a super fancy approach, which is, everyone is using the word bird. Not everyone is, but actually very few of us understand what's inside. This is this bidirectional attention network, which is using very fancy feature, which are neither words nor syllables. It's something in between, and it is claimed that this bird can do any language you can imagine. So this is very fancy approach that we are happy it exists. But the question we ask here today is, do we understand what's inside? Because yes, that's right, that we can get an improvement. If you want to do a better authorship attribution, then take, out of the shelf an algorithm such as doc2vec or seek2vec. There is plenty of those. And you'll have it. You'll have a better authorship attribution. But what we want to ask here today is how these embedding models, how this context-aware models actually improve, and if they improve authorship attribution, what makes them improve the final scores? That's the actual question we are going to ask today. And we are taking one step back, so that we start with a very, very simple word embedding model. And before we go any further, there's a very, very short introduction to distributional semantics I'm going to provide, or distributional models. We are going to use them. So distributional semantics is relying on the so-called distributional hypothesis, which basically says that if you take a big corpus, and it's from this corpus you extract sentences, and there are two different words which appear in very similar contexts, you can say that these two words have something in common. So it can be formalized as a degree of semantic similarity is a function of the overlap of the context, right? So the more the adjacent words reappear in different contexts, the more they say something about the similarity between the two words in question. Right? And now how it works, this is a very, very simple, super easy explanation of the distributional semantics methodology, how those models work. So let's take a text, let's take a corpus, because we do need a very, very large corpus, but let's assume that this corpus begins with with a particular novel. In this case, this is The Hand of the Baskervilles by Arthur Conan Doyle, and it starts with a text, right? So this is a text, and now what these models do, I'm oversimplifying, but you can assume that what these models do, they trace all the situation in which Mr. and Sherlock co-occurs, in which Sherlock and Holmes co-occur, in which Holmes and who was usually, these word pairs are being extracted and put in a very, very long sequence or list. And this list, in this list, you've got all the possible combinations of those words that co-occur. So whatever is captured within a context, it is being put in this list. And this list can be, really long, like more than 1 billion elements can be put on this relatively short list, because we are dealing here with only 100 English novels. So this is a very, very small corpus, and still the number of elements might be absolutely gigantic, right? And that's the problem that distributional semantics usually struggles with, right? The amount of data. So there's a much better way of representing this kind of data abundance, and this is using a table of the co-occurrences. So as you can see here, we've got a square table of 36,000 by 36,000 elements, because that's the size of our vocabulary in our corpus. And the word apple and the word morning co-occurred 5 times, being adjacent one to another. Late and morning 12 times. Table and late only once. Banana and breakfast 3 times, and so on and so on, right? So it's not you, the computer does it for you. The computer records all the co-occurrences between those adjacent words, right? And the problem is that this is quite a big thing, but we are already there. This is already a distributional semantics model. So we can say that the word tea, for example, can be defined as its position, its numerical position against all the other words in the vocabulary, right? So the word T can be represented as a vector of 3, 5, 2, 12, 9, and so on. You've got those numbers here, right? Of course, this is a very, very long vector of more than 36,000 elements, but still you can define the word T as such a vector. And interestingly enough, if you compare this vector to, say, hour, they will be quite distant apart one from another. And if you compare tea to, say, coffee, they will be very similar. And that's what this distributional semantics can do for you. It retains the context, it retains the information about the context, and it retains the information about the semantics of the words. And now, speaking of the applications, you are probably familiar with the word-to-vec, with the word-to-vec algorithm, which is a very, very well-known method of doing the embeddings with neural networks. But there is another one that the one that we are using here in this project. This is GLOVE, and this is a simpler model. You know, the final effect is very much the same, but the computational phase is slightly simpler because there is a matrix decomposition rather than neural networks training. So we'll be using this GLOVE. What it does, because the problem we are dealing here with is the size of this table, which is absolutely enormous, gigantic, like 36,000 by 36,000. Who can deal with such a big table? No one. No computers could. Now, perhaps some of them can, but even though the idea was 7 or 8 years ago when this word-to-vec algorithm was announced, to squeeze this huge space into, say, just 100 dimensions. It's not words anymore. So the word T is now defined as its position in this multidimensional space, defined by those 100 dimensions or 100 values, rather than 38,000 words, right? So that's the only difference, but the original information is still stored there, right? What I mean by that is that if you draw such vectors for tea, for tablet, for breakfast, I'm taking just the numbers from here, you will see that tea is less similar to table than table is to breakfast, right? And using those vectors, you can define the semantic spaces in this model, which is very, very useful, which is we hope, very useful for authorship attribution, because not only you deal with the frequencies, but also you can enrich them with the context, because this context, the knowledge about the context is still retained in those final vectors. Now, stylometry or authorship attribution, on the other hand, not on the other hand, but stylometry, what it likes to do, it likes to deal with a very simple setup where every single text, say we've got 3 books by Buckley and 2 books by Bennett, each book or each text being, or each sample being represented by a vector. So we are at the vectors, but this is a different vector, and that's the issue. Being represented as a vector of frequencies of those particular words, frequent words, not so frequent words, whatever, right? So Bennett is represented as a frequency of the word the in this text, and 2 of, and so on, right? And the particular word, say word A, is a distribution of different frequencies across the corpus. But what is super important here is that stylometry is interested in particular texts, whereas distributional semantics methods or models are interested in the meaning of a word in total, right? So rather than having A represented differently in different texts, what distributional semantics wants to do is to extract the general knowledge of the A, right? So the problem we are facing here is how to train the model, the distributional semantics model, and to still keep the information about particular texts, right? So this is too contrasting, that it cannot be joined, it cannot be combined that easily. Of course, some approaches have been already done, and we are inspired by some of them. So what we do, we use the idea of a sponge words, as we call it. The sponge words being one word at a time, being identified to be trained in the model. So we train a word-to-vec model or GLOVE model, word embedding models, in which we replace the original word, the word the, for example, in the first case, by its representation in particular texts. I know I'm not clear enough, but here's an example. So what we do, in this first text in the corpus, we replace every single the by something else, the Doyle one, right? That's an ID. It doesn't need to be the Doyle one, but for the sake of convenience, we use a very, very, very meaningful replacement, right? So we replace the these with something else, and we do the same for, say, Berkeley, the in Berkeley, the in Austin, the in Dickens, you name it, right? And then we train the model so that it does not see the as a general word in a corpus, but it sees the as being defined differently in particular text, while, that's important, while keeping untouched all the other words, right? So all the other words in our corpus, all the other words in our model are being stored as in the original, right? So we just focus on this one particular word. And now that's our model. So not only do we have this morning, table, and breakfast, but also the being broken down into particular these, right? So that's the model we end up with. And Artyom in a minute will show you how this model can be read and what can we learn about that. But let me just finish my part with this idea how we fit the stylometric, for example, the supervised classification model with this information about the different these. So we simply keep the these, right? As defined by those 100 dimensions, and these are being treated separately for every single text. So that's the combination of the two, the combination of what the embedding model can do for us, and the combination of what stylometry likes to have the data formed, right, or formatted. So there is a combination of those two approaches. I think that's all for me. And now, oh, sorry.
Yeah,
now,
it's my ship now, Maciej.
Yes, I have to stop sharing.
So I will quickly share the slides as well. So I think everything could be seen. So the intuition behind the identity vectors or sponges, as Maciej called them, that if we take them in one model against all other words, that their immediate neighbors would be another sponges because their usage and distribution in a text are similar. And this is indeed, if we take the nearest neighbors of the vector z Blackmore 1, this is like an identity vector, and we measure the cosine similarity and sort the words by the cosine similarity, we indeed see that the closest vectors are the other sponge words or sponge vectors from another novels by Blackmore. We also see, however, that this list also includes the common words, which means that these identity vectors, they still do participate in a global semantics, and we still should expect them to participate in the global semantics as well. There's nothing surprising about that. And you basically can treat this list of words as a keyword list, because obviously the similar words to identity vectors or the sponges would be words that co-occur similarly with words that the identity vectors co-occur. So what we can do, we can take the small portion of the whole semantic space of the whole model, and we can project it to the dimensional using the UMAP in this case, but it really doesn't matter. So sorry about this a bit busy plot, but there is two takeaways to have it from here, right? So this is the model that is trained with identity vectors or sponges that uses the word as this identity embedding. Right, so what you can see that the obvious clustering by the author, so the authorial signal is picked quite immediately, but they also participate in this gray words space that could be seen as the keyword space, and the embedding, they kind of pull a bit the semantic space of this, the neighborhood semantic space of this identity vectors towards the nouns and obviously characters, because characters, again, the stuff that co-occurs uniquely similarly to how the co-occurs uniquely within this text. And we know that using different models for different words for this identity vector. So if we build another model that would use not the z word but the to word for this textual representations, this space would be a little bit pushed in a different dimensions and include more verbs that you would expect to occur with to, but also characters and persons and and pronouns and the stuff alike. So this kind of concludes our kind of brief exploration period, and there are two things that that really matter in us. So first, as I repeat, so the first thing is the clustering by authors, and the second thing is kind of participation in the global spaces. So you can treat this global space similarly to to the words that are distinct, to the words that are distinct to the texts, and the distribution of authors would be somehow related to the global semantic distributions, to the global semantic space of the model. Okay, so what we want to do, of course, is first to formally test this brute force approach to text embedding for authorship attribution. So later we can do the unspeakable atrocities that we advertised before in the abstract. So the outline of this experiment is very simple. We take this one identity feature at a time. We build one glove model for each identity embedding. So we have, you can build basically identity embeddings for all the corpus, but we use this cutoff of 200 most frequent words. So we will have 200 models that uses different embedding, different identity embeddings. And we just use 200 most frequent words. And for the classification, we use the supervised scenario with the support vector machine. We used the well-known 100 English novels benchmark corpus, which is, again, it's not something we are not using to as Maciej said, to provide you some mind-blowing state-of-the-art performance or something like that, but just to this benchmark corpus is nothing like, so it's not a rocket science to attribute. And we do the stratified cross-validation on 1,000 iterations, where the test and the train vectors are picked randomly in each iteration across the whole corpus. So if we look at the 60, not 200, but the 60 most well-performing identity vectors and arrange them by the performance, you would see immediately that the best performing models are also including the words that are most frequent in English, right? So this is the words of like of, the, and, to, a, and so on. And this kind of pushes us to model this relationship formally. And if we take the whole 200, the performance of 200 models in our classification experiments, then you can easily fit a nice regression that would show a clear decay of accuracy dependent on the frequency. And this is quite revealing because it hints that the frequency is, in this case, is the main, the frequency of the identity embedding is the thing that drives the accuracy the most, not the positional information, or maybe not exactly the positional information that sponges capture in text. If this is true, it would be possible to completely randomize the position of the sponge, as we think, and control its frequency absolutely manually, which obviously opens a whole new rabbit hole of like dizzying questions of how to model the word frequency that never existed. But however, what we want to do in this experiment, second experimental setup that kind of randomizes the position of informations of the identity embedding, is to just create a dummy word, that has never existed in a text, and just place it absolutely randomly through all of our text. The idea being that we just need the frequency to, seed this word to how many places, so the context could be soaked into this dummy sponge in this case, and it won't be tied to the specific functions of the word or specific occurrences of the words that are used when we do this kind of frequency-based, word-based identity embedding. So as you see now, our vectors of interest would become this embeddings of absolutely dummy words, just the soak context locally in each of the texts. And again, as I promised, the mind-boggling question of how to determine the frequency of a word that never existed. And we here play with several approaches that are not very optimal. And this is itself a very interesting problem, because obviously the language has like informational, it is informationally efficient, and couldn't be a word more frequent than the "the," for example. So we play around kind of tying the frequency of this dummy word to the "the" in several flavors. It could be tied to the original "the" frequency in a given text. There could be a constant "the," which just plays the frequency of the dummy word on the maximum "the" in the corpus, maximum observed "the" in the corpus. We can just model the normal distribution based on the standard deviation and pick randomly this frequency. So we efficiently kind of untie this frequency from the given author or a text. We can just specify an arbitrary constant that would be a higher frequency than the "the." Let's say it could be 8% of each text would be a dummy word. And our kind of the more formal approach to modeling the word that is more frequent than "the" is kind of, you can imagine it as a modeling of the intercept of the linear model of the rank to frequency to rank linear model. So what is the frequency of the rank 0? And it's not exactly the same, because frequency of the rank 0 doesn't exist, because the exponential super high growth, and usually this word is estimated to be larger than the whole text. So we do some tweaking there, and please ask us about this later so we can discuss it in more detail, but I won't spend too much time discussing it. It's a hacky solution, again, just for understanding and kind of having some formal ground to model this frequency of the dummy word. So we repeat the same procedure of classification now with this dummy embedded words, and what we can see is that the intercept and arbitrary constant, the setups, the experimental setups where the frequency is boosted, the frequency is larger than the "the," it can even outperform the previously seen vectors of and "the" that achieve like median accuracy of 90%, let's say, and they even boost this because the frequency is boosted. So what we can take from here is that the randomized position of the sponge doesn't seem to have any effect on the authorship attribution here. Based on that, we can also assume that this relative space, that the keyness space doesn't really matter. So we are going back from our context representations and contextually aware representation of the text. We are kind of pushed back to the sheer frequencies. And obviously, you can assume if we already randomize the distribution of the identity word, if we randomize the text and shuffle the text, absolutely breaking all assumptions of distributional semantics, it also wouldn't have a large effect on it, or would they? And the reference to Mortal Kombat represents what we think we do to the distributional models, but obviously language is much more versatile than we think, and the frequencies would still drive the classification based on the identity vectors to success. So we now absolutely randomize the dummy position of the word. We keep the dummy setup the same as it was before. We now shuffle the whole text. So the global semantic space is basically efficiently destroyed in the models. And so what we get is basically that so there's no global semantic relationship, the context is destroyed, but we still, that it doesn't confuse dummy sponges, and they still prefer confidently in authorship attribution context. However, if you look at the global semantic vectors, if you, for example, compare the neighbors of the word book, you will see that in a vanilla model, in the previously used model, it makes sense, and in the shuffled model, it basically does not, and is just spitting at you the words that are occurring frequently with the larger context of the text with this book. This leads us to a simple conclusion that whatever is picked just from the word frequencies in a given text whatever is picked from the word frequencies, and the text in this case just serves as a macro context for word appearances, and it's basically the same as estimating the word distribution from just the sheer frequencies of them. And obviously, there's like a bonus experiment to corroborate what we are already doing, is what we can do and push word embeddings to even more extreme context, is we can do the replacement on non-frequent words. So all the words that are outside of 500 most frequent words we replace with this null. And this now, this excerpt from Conan Doyle becomes absolutely unintangible and something that you don't, and it also sounds like very obscene, something that you don't want to read with kids. However, you know, that the most frequent words are kept there. And in this case, we just use the null, this replacements as the identity vectors. Just to quickly show that it still works, obviously, because we remove words that could be, you know, used for overfitting the text-specific words that could be used for fitting the previous models. The accuracy obviously drops, but it's still highly over the random baseline, and it's still performing over like 75s, 80, around 80% of accuracy. And what we also get from that is that reshuffle. So we build this model in the two flavors. One is the original, preserving the original word order, and the reshuffled, the randomized word order here as well. And what we take from here is that the reshuffle models actually works better in this context. And the explanation is probably because when we reshuffle the text, we just you know, distribute the actual words that we use here more evenly. So this, you know, situations where there's a lot of null replacement would influence this the attribution less than that. So it's time to come to a discussion part based on that, based on what we showed. And so the important, I think, kind of lesson to from what we got here is that text level embeddings, at least in our setting, which is a simplified text level embeddings. However, it still does have topological relations to, for example, to doc2vec procedure that adds the identity vector of a paragraph, for example, or a sentence to the word, to the estimation of the word probability. So it's topologically similar. However, we also can see that our text level embeddings work not because we do have access to the local context of the words and the word proper order. They work, and we assume that this word order is somewhat important. It is not, as we see. They just work because we do have access to the words, right? And if you see this context sponges or word sponges, is basically effectively the same procedure as having the word frequency vectors and not dealing with the word embeddings models at all. So what we see is that the contextual information, at least in the sense of the word embedding and word co-occurrence with each other, the contextual information has limited influence on style recognition. Thus, in our very simplified setup, that is not, again, is not for you know, making some state-of-the-art results. Of course, semantics is never fully eliminated from this equation, and we do not want to really argue that because, you know, that still there remains a lot of words that are heavily preferred in certain contexts, or in context in the sense are the text themselves. So, for example, you know, even if you randomize the whole text, the word "see" would be present preferably in some of the novels, not across the whole 100 novels, with the text that deal with the sea and travels and well, colonial imperialistic literature. Anyway, so if our next kind of point, if the style could be recognized from the sheer frequencies of words, then it may be seen partly independent from the language functions, for the high order language functions such as the messaging, the context, the meaning of the words, which is of course not news in the stylometric thinking and linguistic thinking of style, that the style, it leads us to the question, like, again, returns us to the question, what if we can model the style as a random effect in some true distribution of the linguistic elements? And of course, you know, again, this is a far-fetched conclusions that does not immediately you know, arise from the experiments that we showed us, but of course we cannot resist these far-fetched conclusions. And in terms of separating the style from the content, a lot of things are to be picked from the style transfer in images, right? The classical example that now we have everyone this application on our phones and could do it ourselves is the style transfer in images. So for example, the image could be the image could be kind of dispersed into the stylistic representation and the contextual representation of the content, so they could be taken apart and then mixed together in a new setting. And this leads us to the question of the style transfer style transfer in text and the adversarial stylometry, which are the two fields that we think are not married well enough, because in classical style transfer, very complicated methodologically literature, the style is usually understood as some very weird kind of ad hoc situation, and it could be even understood as like negative and positive reviews. So there's like modeling of taking the positive review and transforming it to the negative review, and they still call it like a style transfer. And our results, again, we don't want to say that the style, we don't want to be this old person that screams at neural networks, and we absolutely do not do not be seen as such. However, it paradoxically kind of brings us back to thinking about the style in a more like explicit, like engineering way. So what if we can also separate the low level features in the stylistic features and high level features into the contextual features of the text? Could we be closer to this adversarial stylometry setups and anonymization setups, when we can say, for example, we can switch on the Tumblr and suddenly everyone will write as Charlotte Bronte, for example, in every our email. So that's all from us. If Maciej wants to add something, we'll be very happy. So let me stop sharing.
Well, totally. I want to add, thank you very much for listening, and thank you very much for being with us, and we wait for questions.